Okay, in this video we'll discuss the factors that affect reaction rate. There are 5 things that can help speed up a chemical reaction, and we should learn all of those today. Right, first thing, you can increase the concentration. Now, increasing the concentration will increase the reaction rate because there will be more collisions. You'll have more particles, and so there's a greater likelihood that those particles will collide with, or the reactants will collide with other reactants. So for example, here you have a certain number of particles, and every time this red particle hits, you see it turning. And so since there's fewer particles in this picture than there are in this picture, you see less collisions. Here you see more collisions because there's more particles. Kind of like being in a crowded room. If there's less people in the room, you're less likely to bump into someone. This increases how fast the reaction occurs because it increases the frequency of effective collisions. So it doesn't make the collisions more effective, it just increases the fact that there might be more collisions that have the correct orientation and have the right amount of energy. Okay, I'll show you a quick demonstration in this video of elephant toothpaste. If you've ever seen it before, great. But this is going to explain it in terms of concentration.
Fast, 2 molecules. Today we're going to talk about chemical reaction rates, which is how fast chemistry happens. How fast 2 molecules might bump into each other and become a new kind of molecule. And there's a lot of different things that can affect how fast chemistry happens. Today we're just going to focus on concentration. And to do that, we're going to use an old standby chemical demonstration called elephant toothpaste. What I have here is some hydrogen peroxide and some sodium iodide, which is kind of a salt kind of thing. Mix the two, and this should create a lot of bubbles of oxygen over here, and it'll foam up and be all really cool and exciting and be wicked fast. All right? Ready? Here goes nothing. Oh yeah, look, there it is. It's bubbling. Ooh, bubbling away. Now this is 3% hydrogen peroxide. What you could buy at the store if you wanted to clean out a cut or something like that. Be careful with hydrogen peroxide because it gives off oxygen gas. So you can see here it goes. It's still bubbling off. Oxygen gas is coming out in a little foam. And I put a little bit of soap in there, dish soap, and that's going to make this cool little foam. And it's still going. So pretty cool. And we just may have to put this on stop time. And remember, this is 3%. 3% hydrogen peroxide. It's still foaming, and it's going to make a mess now. There it goes. Ooh. Classic. Maybe I'll go, oh here, look. You can see it filming over the side, huh? Beautiful. 3% now. Yeah. Still going. So this is a reaction rate, right? The more hydrogen peroxide that's in there, the faster this should happen. That's one of the things about concentration. The more of a substance, the more concentrated a substance, not just how much it is, but more concentrated, the more likelihood that 2 molecules will collide and then have a reaction happen. So in this case, the salt and the hydrogen peroxide molecules will collide, and then you get a reaction happen. And the more likely they are to collide, the faster the reaction will happen. And since we have less concentrated hydrogen peroxide in here right now, it doesn't happen very fast. Well, this is still moving kind of slowly, very slowly. So we're going to clean this up, and let's try it with 30% hydrogen peroxide.
30% hydrogen peroxide is much more concentrated, so it shall happen faster. There it is. Nice and fast. Look at how fast it's happening. That's because chemistry happens faster because there are more molecules present to collide with each other to cause the chemistry to happen. And when this reaction happens, it causes bubbles, so we get lots of bubbles when it happens fast. So 30%, it happens really fast. Now let's just quick back it up and just compare one more time the 3% to the 30%.
Okay, let's skip that part. So you can see the more concentrated it was, the faster the reaction rate was. It was faster. It's a cool demonstration. Okay, next we're going to talk about pressure, and this only affects gases. If you increase the pressure of a solid, nothing's going to happen to those particles. And so increasing the pressure of something that has gas in it will increase the reaction rate because you're decreasing the volume. So remember from gas laws, there's a direct relationship, inverse relationship between pressure and volume. If you increase the pressure, the volume decreases, or vice versa. If I'm decreasing the volume, as you see in this picture right here, here the volume is decreasing, and so since the volume's decreasing, that's an increase in pressure. You see that the particles are closer together. It's like increasing the concentration. Now there's going to be more collisions between those reacting particles. And then there's a greater chance that those collisions will lead to an effective collision. So this will increase the frequency of effective collisions with enough energy. It's not changing the energy, just the amount of collisions. So there's a greater chance that there will be more collisions at the right energy and at the right orientation. Okay. Third thing is increasing the temperature. You can see how fast these particles are moving here. Cold particles don't move as fast as hot particles. And so you can increase the reaction rate by increasing how fast those particles are going. We say that temperature is how kinetic energy is measured, so we're increasing the kinetic energy of the particles, which should bring us back to the reaction diagram. If you increase the potential or kinetic energy, you're giving it enough activation energy in order for it to react. So here we'd be giving it the reactants enough energy to get over the hill and start to form products. Okay, it also increases how many times it will collide, and so there's a greater chance of there being effective collisions with enough energy because of the temperature and lined up properly, the right orientation. Okay, here's a video on glow sticks. She's going to show you cold water, room temperature water, and hot water, and you can see how fast the reaction happens. Now remember, in a glow stick, what you're doing is you're snapping the little glass container inside the glow stick. That little glass container is holding a reactant, and so when that reactant is exposed to the rest of the reactants in the glow stick, you get the glow that you're looking for.
All right, so we're going to look at how does temperature affect the rate of a chemical reaction. So here I've got 3 different samples of water. I have cold water, just ice. I've got some room temperature water. I've got some hot water. And the chemical reaction we're going to run is actually what goes on inside a glow stick. So what I'm going to do first is I'm going to break the glow sticks so the reaction starts. You can hear them crack there in the background. I'm going to shake them up so they start to glow. Ooh, okay. I'm going to put one in each of my water samples. And so we're going to be looking at how bright are these glow sticks. So here's the cold water one, a little closer. Here's the room temperature, that's kind of our standard there. And here's the hot water. So I'm going to pull back again so you can see them all at the same time, so that you can see the difference between all 3 cups.
Okay, you should see that the hot water is glowing brighter because those molecules have more kinetic energy, so they're producing that product at a greater rate. Okay. Fourth thing is increasing the surface area. Now we have to go back and think about what surface area is. Surface area is just the outside. So here's a cube. And so the surface would just be all the sides of this cube. Okay, so if we were to cut this cube into 4 pieces, now we would be exposing more of the inside of the cube. So we'd have this section here on both sides that would be exposed, and then here, 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 and then back here. here, and the same for the other cubes in the back. You have more surface exposed if you cut the cube into more pieces. So if I keep cutting, I'm going to get more and more surface area. So if I decrease the size of the particles, I get an increase in surface area. And as I was saying, it exposes more area for that reaction to occur. And the reason for that is it's increasing the frequency of effective collisions. Remember, those collisions need to have enough energy and they need to be lined up properly, but if you increase the number of collisions, there's a greater chance that that'll happen. Okay, he's going to do a great demonstration of surface area.
Surface area affects the rate of a chemical reaction. Here we have some lycopodium powder. I'm going to place a small amount of it onto this ceramic plate. I'm then going to show you with the Bunsen burner flame that this powder really does not burn in the form that we might expect it to burn as a very flammable powder. And yet, when we allow this powder to sift into the flame as a dust, we've increased the surface area around each particle, and the oxygen concentration around each particle increases. Let's do that now.
Okay, that was a great demonstration of how increasing the surface area increases the reaction rate. I'm not going to do this demonstration, but I'd like you to think about this one. Which one would burn quicker? Would it be a cinnamon stick or cinnamon powder? And you should have said cinnamon powder because of its higher surface area, more areas exposed so that it can react with oxygen and form flame. Okay, fifth thing, the addition of a catalyst. Now, I've talked about this just a little bit, but a catalyst can speed up the reaction by lowering the activation energy. What it does is it provides an alternate pathway for that reaction to occur. And so here I've got a picture of a potential energy diagram, and you have a person trying to put a boulder over this hill. Now, as he's lifting it over the hill, it's a lot of hard work to do that. Now, the end product is this smashed boulder. That is this top part, him walking without a catalyst. If he had something like a catalyst, like an enzyme here, like this wheelbarrow, that's going to lower the activation energy. It's going to lower the amount of energy that it's going to take to get over that hill. The nice thing about a catalyst is it does not get consumed in the reaction. It doesn't get used up. And so you'll see it sometimes written over the arrow to say that it's helping the reaction happen, but it's not something that's part of the reaction. It's not a reactant. It's not a product. It's just something that assists in the reaction. So after it's done, it can move on and help some more reactants. So it continues to do work. Here's what that would look like in this picture down here. You have a catalyst. It's bonding to two reactants. And then what it does is it brings those two reactants together, and now they're bonded together. And it moves on and does it for something else. Now, an enzyme, something you learned in biology, is a biological catalyst. It works the same way. Here's an example of an enzyme bonding to a substrate. And what it does is it breaks into that transition state. It breaks them apart, and now you have products. So you have a lot of enzymes in your body that help you break up things like food. For example, in order to break up lactose, some people are lactose intolerant, you need the enzyme lactase. And so if you have lactase, if you're a good producer of lactase, you have no problems. You break it up into galactose and glucose and you move on. If you're lactose intolerant, you cannot break up that lactose, and instead in your intestines that lactose starts to ferment, the bacteria causing pain. The opposite of a catalyst is an inhibitor, and what it does is it slows down the reaction. Okay, it could block a reaction from happening. So what the inhibitor will do is it'll bond to something instead of letting the two reactants bond. For example, an inhibitor would be this compound. This is something that sends a signal to your brain that you're in pain. Well, pain relievers work by blocking that compound and not allowing your brain to feel pain. Okay, the next part of your notes, I'd like you to watch the next video. How do you speed up a reaction? And what you're going to do is you're going to quickly write the analogy for each factor that affects the reaction rate. So watch the next video, add it to the bottom of your notes. I hope you enjoy that video. It's great.